Assalamu alaikum wa rahmatullahi wa barakatuh. This is Alia, and inshallah we will continue discuss about congruence in lecture 2 from ITDR2103. In today's lecture, we will discuss about modular representation of integer, which is sum of modular representation, and special congruence theorem like Fermat's little theorem and Euler-Phi function. Now grab everything you need beside you and let's start this session. So, modular representation of integer is when I have m1, m2, mk, and they are relatively prime integers greater than 2. Then m is equal to m1 times m2 times mk. And we have a1, a2, ak as a positive integer, and they are greater than 0 and less than m. And in h1, each ai is greater than or equal to 0 and less than mi, and we have this system of congruence. Then we can use Chinese reminder to find the unique integer less than m that satisfy the above system of congruence. If b is greater than 0 less than m and b is the solution, then from the following system, congruence system, and by using Chinese reminder we got that b is congruence to a mod m, then we can use the following representation to represent the system congruence here. So we says that a1, ak, a2, ak equal to x mod m1, x mod m2, x mod mk. Then a can be represented using a mod m1, a mod m2, a mod mk. And put in your mind the result here is the reminder when I divide a by m, and here and here. Let's see this example to just explain whatever we said earlier. Now here we need to find the modular representation of the integer 25 with respect to modulo 2, 3, and 5. So to do so, let's just have all what we got here from information. Now let a equals to 25, m1 is 2, m2 is 3, and m3 is 5. Okay, then we can say that m is equal to 2 times 3 times 5, which is equal to 30. Now all of these information are mentioned in my question here. To solve or to find the modular representation, I need to find a is congruent to x mod 2, a is congruent to x mod 3, and a is congruent to x3 mod 5. So let's just substitute the variable here with the values that I have. So when I divide 25 by 2, then I got a remainder as 1. When we divide 25 by 3, then I got a remainder as again 1. And when we divide 25 by 5, then we got a remainder as 0. So from here, the modular representation of 5 is written as like this. So modular representation of 5 is 1, 1, 0 with respect to modulo 2, 3, and 5. And it's really important we mention the modulo respectively. Okay? Now let's check the question here. We need now to find the integer a if the modular representation of a is 215 with respect to the modulo 357. Now I got the modular representation, I got the modulo, I need to just find a. Okay, so let's first find the range of a. So here we got that m1 equals to 3, m2 is 5, and m3 is 7. So from here we can say is that m is equal to 3 times 5 times 7, and this is equal to 105. And now from here I knew that a will be greater than 0 and less than 105. So let's just define the modular representation that we got. Now we got that a has the modular representation that a mod 3, a mod 5, and a mod 7. So this is equals to 2, 1, and 5. Now what do we mean by the following model representation? We mean that x congruence to 2 mod 3, x congruence to 1 mod 5, and x is congruence to 5 mod 7. Now in order to find x, we need to use Chinese remainder theorem. So here we got that 105x divided by 3 is congruence to 1 mod 3, and this is equals to 35x is congruence to 1 mod 3, and this is equals to x is 2. Then we got 105x divided by 5 is congruence to 1 mod 5, and here we got, when I divide 105 by 5, then I got 21x is congruence to 1 mod 5, and here x is equal to 1. Then the last one is 105, yes, divided by 7 is congruence to 1 mod 7, and this is equal to 15 x congruence to 1 mod 7, and here we got that x is equal to 1. Now to find the value of x, we need to continue in Chinese reminder. Now here we got that x naught is equal to 2 times 35 times 2 plus 1 times 21 times 1 plus 1 times 15 times 1. Then all of these mod 105. So here we got that x naught is congruence to 140 plus 21 plus 75 mod 105. So x naught is congruence to 236 mod 105, and from here we got that x naught is congruence to 26 mod 105. So a is equals to 26. So moving to our next point, we can see that we can add a modular representation. In case I have the first modular representation A with here reminder when A1 is divided by M1, reminder with A divided with M, and here we got the third reminder, and B with reminder 1, reminder 2, reminder 3, then A plus A1 plus B1 will give me a new reminder which is C1, and the same for the rest. Let's check the example here. Here we need to find the integer a plus b with respect to modulo 235 if a equal to 11 and b equal to 13. And we will do this in two ways. The first way, we need to find the modular representation of a, modular representation of b, then we add them together. So here we got that when a is 11, then 11 mod 2 is equals 1. Then we got 11 mod 3 equals 2, and 11 mod 5 equals 1. Now the modular representation for a is a, and a here is 11. We got that 1, 2, 1. For b, when b is equal to 13, then we need to find when I divided 13 by 2, how much I got a reminder? 13 mod 3 and 13 mod 5. So when we divided 13 by 2, then I got as a reminder 1. 13 by 3 we got the reminder 1, and 13 by 5 we got the reminder 3. So here is the modular representation of b, and it is 1, 1, 3. Now to find a plus b, and this is equal 11 plus 13, it is 24. Then we need to find 24 mod 2, which is 0, 24 mod 3, which is also 0, and finally 24 mod 5 equals 4. So here we got that a plus b has the modular representation 0, 0, 4, where a plus b equals to 25. Now let's check the second way that we can do. Here we got this too, to find a plus b. So here we got that the modular representation of 11 equals to 1, 2, 1. Then the modular representation of 13 equals to 1, 1, 3. Then A plus B should have the modular representation. 1 plus 1 is 2. 2 plus 1 is 3. Then 1 plus 3 is 4. Now we need to find each one mod. So in case we had 2 mod 2, this is equals to 0. 3 mod 2, sorry, 3 mod 3 is also 0. And 4 mod 5 equals to, again, 4. So here we got that A plus B has the modular representation 0, 0, 4. Now let's try to find what is A plus B by creating the system of congruence where X is congruence to 0 mod 2, X is congruence to 0 mod 3, and X is congruence to 4 mod 5. By using Chinese remainder theorem, then we got that M is equal to 2 times 3 times 5, and this is equal to 30. Then we got here 30x divided by 2 congruence to 1 mod 2, and this is equals to 15x congruence to 1 mod 2, and from here we got that x is equal to 1. Then we got 13x divided by 3 is congruence to 1 mod 3, and here 13 divided by 3 equal to 10x congruence to 1 mod 3, and here we got that x is equals to 1, and finally 13x divided by 5 is congruence to 1 mod 5, and here we got, when we divided 13 by 5 we got 6. X is congruence to 1 mod 5, and here we got that x is equal to 1. Now let's find x naught. So x naught is congruence to 0 times 15 times 1 plus 0 times 10 times 1 plus 4 times 6 times 1. Then we got here that x naught is equals to 0 plus 0 plus 24, all of these mod 13, and here we got that x naught is congruence to 24 mod 13, and from here A plus B is equal to 24 with the modular representation 0, 0, 4. All right. Now let's move to special congruence theorem, and the first one is Fermat's little theorem. Now Fermat's little theorem discussed about a theorem can be applied on prime number, and when I said prime number, then I mean that this number does not have factors except itself and 1, something like 1, 2, 3, 5, and so on. So if we have a modular explanation here, and as p a prime number, then we got that it's congruence to 1 mod p. And it's important to know that p does not divide a. Let's check one example, but before that we got another formula here. Says that a to power p is congruence to a mod p. First, let's prove the first formula, where p to power p minus 1 is congruence to 1 mod p. If p is 5 and a is 12, then we can just rewrite the theorem here. Mod p, and let's substitute the value in the theorem. So here we got that 5 to power, here we got 12 to power 5 minus 1 is congruence to 1 mod 5. So here is 12 to power 4 is congruence to 1 mod 5, and 12 to power 4 is 20,763, and this is congruence to 1 mod 5. How I say the relation there? If I divided 20,736 by 5, then I will get a remainder as 1. And when we divided 1 by 5, then we got again a remainder as 1. Therefore, the relation is there. Now, let's check the second theorem, where it says that a to power p is congruence to a mod p if p equal to 3 and a equals to 4. So here again, we will write the theorem and we'll try to prove it. So by substituting with the values I got here, then 4 to power 3 should be congruence to 4 mod 3. Now 4 to power 3 equals to 64, and 64 should be congruence to 4 mod 3. How we know this relation is there? First of all, we need just to find when we divide 64 by 3, then we got a remainder as 1. And when we divide 4 mod 3, then we got again the remainder is 1. Therefore, the relation is there. Now, let's move to the second special theorem that we got in this session, which is Euler-Phi function. Euler-Phi function basically measures the breakability of a number. For example, phi n is a combination of 1, 2, 3, 4, 5, 6, 7, and 8. Now the function finds the number of numbers less than n that are relatively prime to n. What do we mean by relatively prime to n? We means that they do not have a factor with n. Any factor with n. So relatively prime to n means that the number does not have any factor with n. For example, here we got that 1 is 1 by 1, which is nothing, no factors with 8. Then we got 3, 5, 7. And those the numbers of number that they are less than n and relatively prime to n. Okay, so by using phi function, I got that phi of 8 equals to 4. 4 numbers which are relatively prime to n. Now the function is equal to, when I have a number, then it can be divided to 2 prime numbers. Then each prime number, phi prime number, equal to p minus 1. and here also q minus 1. Okay, now let's check the question here. We need to find the value of phi n. So here we got that n is equal to 15. Now we try to find all the factor of 15 and try to make it a product of two prime number. So for 15 we got that it's equal to 3 times 7, right? Okay, then here we got that p is 3 and q is 5. Now let's apply the function there. So we got that phi 15 is equal to phi 3 times phi 5. This is equals to 3 minus 1 times 5 minus 1, and here we got that it's equal to 2 times 4 equals to 8. Now in 15 there's 8 numbers that are relatively prime to 15, and they are, here we go, 1, 2, 4, 7, then we got 8, 11, 13, and 14. So instead of broke the number to its numbers and then trying to find each one with the factor and then got the relatively prime to n, then we can use only the function in here. Okay. Now if p is a prime and n is a positive integer, then phi of p to power n equal to p n 1 minus 1 over p. Here in case we got a numbers such that phi 8. Phi 8 is equals to phi 2 times 4. Now 2 is a prime number, 4 is not. So I need to divide again 4 to 2. So here we got that 4 is equal to 2 by 2. Then the previous function cannot be used. We can use this one. How so? Let's suppose I have n equal 4. Then I can find the phi of 4 by using the following formula. So here we got phi 4 equals to phi 2 by 2, which is 2 square. Now 2 square, phi 2 square equals to 2 square 1 minus 1 over 2, which is p. Now this is equals to 4 times 1 over 2, and here we got that 2. Let's suppose we got here 8, which is our example in here. Now phi 8 equals to phi 2 cube. This is equals to 2 to power 3, 1 minus 1 over 2. And this is equals to 8 times 1.5, half, equals to 4. Let's suppose we got 16. 16 is equals to phi 16 equals to phi 2 power 4. And this is equals to 2 to the power 4, 1 minus 1 over 2. And here we got that 2 to power 4 is 16 times half. We got that the result is 8. Alright, now if you know that if a and b is greater than or equal to 0 such that the GCD is 1, then phi AB equal to phi A times phi B. And from here we got that if n is equal to P1R1, P2R2, PKRK, where P1, P2, PK are distinct prime integers, then we can use the following function here. So let's suppose we have to find the value of 36. what can we do? We can use this function and the function we just identified earlier. So for using the following, I can got that, first of all, n equal 36, and 36 is 4 times 9, which equals to 2 square times 3 square. So from here, I can use the following function. So here we got that phi 36 equals to 36 times 1 minus 1 over 2, then times 1 minus 1 over 3. Now here we got that 36 multiplied by 1 minus 1 over 2 is 1 over 2, multiplied by 1 minus 1 over 3 is 2 over 3. So here we got that 2 will go with 2. 36 divided by 3 equals to 12. If we want to use the previous one, then we need to find that phi 36 is equal to phi 4 multiplied by phi 9. Now here we got that 4 is 2 square, prime number to power, multiplied by 9 is 3 square. So here we got that 2 square is equal to 2 square, 1 minus 1 over 2, okay, multiply by 3 square, 1 minus 1 over 3. So this one is equal to 4 times 1 over 2 times 9 times 2 over 3, and we got the result also 12. Okay, let's check another example here. We need to find the value of 554. Again, we will do in both way, in the previous one and the one before. So here we got that n equals to 54. Now 54 is equal to 2 times 27. 2 is a prime number while 27 is not. So we need just to find a prime number of 27. So prime factorization. So here we got that 2 multiplied by 3 to power 3. Now here the first way we can just find phi of 54 is when we apply phi 2 times phi 3 cube. So here we got that 2 multiplied by 1 minus 1.5 times 3 cube multiplied by 1 minus 1 over 3. So here we got that 2 times half times 27 times 1 over 3. So 1 minus 1 over 3, we got that 2 over 3. And here we got that this is equals to 18. Now let's try the other function where phi 54 is equals to 54 multiplied by 1 minus 1 over 2 times again 1 minus 1 over 3. And here we got that 54 multiplied by 1 over 2 multiplied by 2 over 3. So here we got again the same answer, which is 18. Okay, here we got that let n equal 900, then find the value of phi 900. So when we got that n equal 900, which is equals to 4 times 9 times 25. And those are not a prime number, but we can just do the prime factorization here. So we will got that 4 is equal to 2 square, 9 is equal to 3 square also, and 25 equals to 5 square. And here we got all the numbers in prime. Okay, now let's just apply the function we got, where 900 equals to 900 times 1 minus 1 over 2 times 1 minus 1 over 3 times 1 minus 1 over 5. So here we got that 900 multiplied by 1 over 2 times 2 over 3 times 4 over 5. And here we got that phi 900 equals to 900 times 4, 3 times 5, since 2 will go with 2, and this is equals to 16 times 40, and here 4, and here we got that phi 900 equals to 240. One more theorem. Let a and n be integers such that GCD an equal 1, then a to power phi n is congruent to 1 mod n. And here we need to prove the congruence if we got as n equal 12 and a equal 17. So first we need to find the GCD between 12 and 17. Now the greatest common divisor between 12 and 17 is 1. Then we can apply the following theorem. So we need first to find phi 12, which is equals to phi 4 times 3. And this is a prime number. This not, so just make it a prime. So this 4 equal to 2 square times 3. Now just distribute the phi. So we got here phi 2 square times phi 3. And this is equals to 2 square, 1 minus 1 over 2, multiplied by 3 times 1 minus 1 over 3. So here we got that phi 12 is equals to 4 multiplied by 1 over 2 multiplied by 3 multiplied by 2 over 3. So here we got that phi 12 is equals to 4. Now applying this theorem here, we got that a phi n is congruent to 1 mod n. So a is equal to 7. Phi 12 should be congruent to 1 mod 12. So here we got that phi 12 is equal to 4. So 7 to power 4 is congruent to 1 mod 12. And 7 to power 4 is 2401. Is congruence to 1 mod 12. And if we check, when we divide 2401 by 12, I will get a 1 a reminder, and 1 divided by 12 getting the 1 also as a reminder. Therefore, 2401 is congruent to 1 mod 12. And here we reach the end of this session. We introduced the modular residue representation of integer, and we saw how we can have the sum of modular representation. And then we discussed about special congruence theorem, Fermat's little theorem, and Euler. Fine. Please feel free to ask any question if you have in the comments or sending to me by email. Thank you. We'll see you inshallah in next session.